How many of you at some point in your life heard, and probably heard many times, that a negative times a negative is equal to a positive? But we're never told why the statement is true. My name is Max von Neumann, and I'm here to answer this question for those who were never given a satisfactory answer, or no answer at all. Okay, we are going to hit this idea with 3 powerful cases. The first will just be a quick pattern to motivate us to think deeper. The second example will show the idea in a more logical perspective. And the third case will be more in line with a formal proof. It should be pretty exciting to know that after this video, you will be able to explain to friends, family, or anyone else who wants to know why a negative times a negative is equal to a positive. If anything else, it's a sure way to get kicked out of a party on a Saturday night. So let's go to our pattern. The pattern here, we will be under the assumption that a positive times a negative is equal to a negative. So as you can see, 3 times negative 1 is equal to negative 3. 2 times negative 1 is equal to negative 2, and so forth. Those are the rows of multiplication. Now, pay attention to the column. In the column, you can see that in the first column, we are decreasing by 1 unit. It goes 3, 2, 1, 0, negative 1. In the second column, it's a repetition of negative 1s. And in the third column, we are increasing by 1 unit. It goes negative 3, negative 2, negative 1. So if we look down here at the last row, we have a negative times a negative. Well, if the pattern proceeds, we should get that a negative 1 times a negative 1 is a positive 1. It appears by our pattern example that a negative times a negative will produce a positive. Although interesting, it's not a good enough answer for most people. And if you're one of those people, I'd have to agree. So let's take a look at this another way. The other way, and a way to really understand this, is by first defining what we are doing. Many of us, when we learned multiplication, memorized it, but we really didn't bother to define it. By giving rules to the idea of multiplication, it makes our world of mathematics more clear, not foggy. So our definition will be as such. The first number will represent groups. If it is a positive group, we will add, and if it's a negative, we will subtract. The positive will be represented by the green, where we're adding groups, and the negative will be represented by the red, which will be subtracting groups. Now the second number is going to represent the pegs within the groups. For instance, a negative 4 here, a negative will be represented by the red, and we will put 4 pegs within each one of the groups. And a positive 4, for instance, will be green. So what we will do is we'll put 4 green pegs within each group. So let's do some multiplication problems so you can see how this game plays out, and you can really get the theory, or you can really get the definition sunk in. All right, so the first one is 2 times negative 4. So 2 is a positive. We think of that as adding, but it's in the groups. So we're looking for 2 green circles over here. So we put up 2 green circles, and then we say times -4. That will be red. So we are looking, remember, these are the pegs. So that means there are going to be 4 pegs within each of those circles. So we have to, we're adding to the group, so we put 4 in here, 4 pegs in there, and we put 4 pegs in there. Now, the green means we're adding to the total group. So we put our complete our pegs here. And if you'll notice, there's no green to neutralize these. There's no green to neutralize those, so there's 1, 2, 3, 4, 5, 6, 7, 8. 8 red. Red represents negative, so the answer is going to be -8. So let's go over here. And as you may remember from your school, that a 2 times -4 is a -8. But now you have seen it by definition, by rule. All right, so now we're going to go to the next question. But in order to go to the next question, we have to neutralize and go back to 0. Okay, I thought I'd step in here and restate some of the rules. Regular size Max, could you move to the left a little bit? Thank you. All right, quickly. The strip or string of green and red pegs at the top of the board is our total. An equal number of green and red pegs at the top is neutralized and gives an answer of 0. We can either add pegs or subtract pegs from the total. For green circles, the pegs come from below the whiteboard and we add them to the neutralized total above. For red circles, we subtract the pegs from the neutralized total above. Peg color is dependent on the sign of the second number, as you know. I think that clarifies the rules a bit more. Max, stand still if you agree. Okay. Continue with your objective. So let's take our pegs out here. Okay, all pegs out and group rings back down. And we look at -2. So a -2 is a group ring that we're going to subtract. So that means I'm going to get a group ring that is red, and there's going to be 2 of them. Hopefully you're kind of following the pattern here. So 2 reds. Reds subtract group, so we're going to subtract from our total up here. Clear that out. Okay, everything's neutralized, so we're at 0. So we have our 2 rings, and we're putting pegs in that are green. The pegs are being subtracted from our total. So let's circle this. So we're going to put 4 pegs in, but we're subtracting groups, so we're putting 4 pegs in each one. 1, 2, 3, 4 green there, and 1, 2, 3, 4 green there. These are going to go away and ultimately leaving us with an imbalance here, which is 1, 2, 3, 4, 5, 6, 7, 8 reds, which are negative, which is negative 8. Now I did that purposely because I wanted you to see that we got negative 8 in both cases. We got negative 8 in both cases, but for a different reason. In this case, we had 2 rings, and the rings were green in this one, and the rings were red in this one. So we got them for different reasons. One time we added to our total, and the other time we subtracted from our total. But we still get negative 8. And again, you can also think of the commutative property as well, that 2 times negative 4 and negative 4 times. So a negative times a positive, positive times a negative is still going to ultimately get us a negative. All right, so now we need to neutralize up here again to start off from 0. And this is the moment you've all been waiting for. You can already probably see it, but if not, don't worry about it. It's going to be here in just a brief second. I have to just set this up and neutralize our red pegs up here. Okay, so everything's neutralized. Our group rings are gone. So we are starting our problem at 0. Okay, everything's neutralized. And I have a negative times a negative. All right, so a negative 2 is a red group ring where I'm subtracting. Okay, so I am subtracting red group rings, which means I'm subtracting from the total up here. But I'm subtracting, let's call it a debt. So I'm subtracting 4, so that means in these 2 group rings, I'm going to have 4 reds in each one, because remember, your negative is represented by the negative is represented by the red. So I'm going to put 4 in here, and 4 pegs of red in here. And those will go to the debt bank or to the overall bank down here. And what this is leaving us is an imbalance up here. But our imbalance is green, which means it's a plus. And we have 1, 2, 3, 4, 5, 6, 7, 8 plus 8. Showing that a negative times a negative is a positive. A way to think about it is you're saying that someone's coming in and they're subtracting your debt. So if they subtract debt, you're going to have more money than what you started off with, if you think of it in a money type world. So let's write that down so we can come to this conclusion. A negative 2 times a negative 4, keep grabbing that wrong pen, is a positive 8. Again, you're subtracting your debt, giving us a positive 8. So now we're going to have you guys think about this one in a second. It's going to be a negative 3 times a negative 2. While I'm setting this up, start thinking about not what the answer is, not that the answer is going to be 6, but think about how you would do this with the group rings. Hopefully you'll be able to show people yourself how to do this. Okay, so I'm going to offset the imbalance to get us back to 0. And get rid of our group rings. Okay, so what we're looking at now is we're looking at a balance of 0 again. Everything's offset. Everything's counterbalanced, however you want to look at that. And we're going to look at this, and so you're probably a step ahead of me since I was setting this up, but I have a -3. Well, -3 is a negative group ring. It's a subtract, so I'm going to circle that in red. I need 3 group rings. I just happen to have 3 group rings over here. So I'm going to grab these 3, put them up over here. Now, what's within the group rings? What's within the group rings? Oh, there's going to be 2 pegs within each group ring. And what color are the pegs going to be? They're going to be red because I have a -2 here. So that means I have 2 red pegs within each of those group rings. I take them from my total here, put 2 in here, put 2 in here, and put 2 in here. Okay, so there's the 2 within each one. We look up here and we say, what's the imbalance? How much of, do I have more green or more red? It's obvious I have more green, so I know my answer is going to be positive. I'll put a plus here just to emphasize. And then I count my pegs. 1, 2, 3, 4, 5, 6. By multiplication, a -3 times a -2 is a positive 6. Another way to show that a negative times a negative is a positive. The next method I'm going to show is more like a proof, and we'll be doing that in... So now that we know logically why a negative times a negative equals a positive, let's look at a more formal approach. Remember, a lot of good tactics involve the numbers 1 or 0. In this case, we utilize 0. With this method, we must agree that distribution is valid. For instance, 3, we know 3 times the inside would be 3 times 9 equals 27. But if we use distribution, this would be 3 times 2, which is equal to 6. And 3 times 7 plus is equal to 21, which is also equal to 27. So using that same idea, let's take a look at what it would be like to take a -3, and inside we're going to put a +4, but then we're going to add a -4. Well, we know that 4 plus -4 is 0, and -3 times 0, anything times 0 is going to equal 0. So we know that this is going to be true. All right. But what if we distribute this? So instead of looking at it as summing the inside and doing parentheses, let's look at it as a distribution problem. So we are going to take a -3 times a +4, and then we're going to take that -3 times a -4. So to re-examine that a different way, we know that a negative times a positive, a -3 times a +4 is going to get us -12. So we're going to put equals -12. And then we're going to add some amount here. Okay, but we know that some amount is going to equal to 0. We already did that part of the problem. Okay, so now if we look at negative 3 times negative 4, the only answer that I could get in here that's ultimately going to get me the 0 that I got when I did the inside would be a positive 12. Now again, remember, we did it the last time we had a negative 3 times the 0, because 4 minus 4 is equal to 0, and that's going to ultimately be 0. That's why we knew this over here would equal 0. So by default, negative 3 times negative 4 must equal a positive 12. So now how can we generalize that in a more formal way? Because this is just one particular example. So to look at it in a more formal way, okay, so in a more formal way, we are going to write A representing any number and B representing any number, but they're both going to be greater than 0. They're both greater than 0, implying that A is positive and B is positive. So that's implying that they are both positive. Okay, so now if we do the same idea that we just did with the specific numbers, we take a negative A out here. So now I know this whole thing here has to be negative because A is positive, but it's a negative A, so that's negative. And then I do what I did with the 4s. I put a B, and then I put a plus negative B. Again, what we're doing is we're generalizing the rule. So now I look at this and I say, okay, let's distribute. That one times that one, and then we're going to get this one. But we know that a B plus a negative B, we know that the inside here has to equal 0. And we know that a negative A times a 0 must equal a 0. So using that same idea and that same approach, that's going to be negative AB plus that box, but we know that ultimately those have to equal 0. So a negative A and a negative B, the only thing that I could possibly get is that's going to offset this negative AB is a positive AB. So A is a positive, B is a positive, and one of them's negated, so this is a negative, so this has to be a positive AB. Therefore, AB, A times B, must be greater than 0 or positive. So A, therefore, A times B must be greater than 0. And greater than 0 is another way to say positive. Hence, as you've heard a million times, and this will be 1,000,001, a negative times a negative is equal to a